Hi everyone, and a warm welcome to the Directions Live webinar series by S3 Malaysia. My name is Caleb and I'm your host for today's session. We will be starting shortly in about 5 minutes. So go get your cup or coffee or tea, sit back and we'll let more participants join in. So we'll see you soon. Hello everyone, and a warm welcome to Directions Live Online. And a reminder before we get started that we are recording today's session and we will be sending out that later this week so that if you want to rewatch it, you have that available to you. And do ask questions, and you can do this at any time during the presentation by adding your question to the GoToWebinar panel on the right-hand side. We've got plenty of time at the end where we will do our best to answer all your questions. Well, now you have joined us today for an industry-focused webinar on the local water supply services on transforming water utility workflows using GIS. We'll be covering some of the angles we intend to tackle in the process of digital transformation. We'll be studying some use cases globally and locally in Malaysia, and we will wrap it up with a take-home message, all in the next about 30 minutes or so. So hello again. My name is Caleb Sang, and I'm a solution engineer with the enterprise consulting team of S3 Malaysia, and am dedicated to the water services industry. So before we dive right in, allow me to make some introductions. S3 has been supporting global water practices to deliver solutions that solve real business challenges and provides real value to water utilities. Now, in the US alone, the top 300 largest water utilities use S3 software to help run their business, as well as more than 7,000 universities and 20,000 cities worldwide. Now, S3 software is being used by more than 350,000 organizations, including 75% of the Fortune 500 and most of the national governments. And we spend 30% of our revenue on research and development, 5 times more than Apple and twice of what Microsoft spends. And 62% of the global water market as of today is using S3 technology. So, in other words, about more than 100,000 water utility workers are using the geospatial cloud to respond to water main breaks, collect information in the field, analyze the water systems, and plan for their capital investments. Now, in water utilities alone, including water supply, water resource, wastewater, and rural supply, we have been serving over 9,000 water customers globally, especially in the Americas, Western and Central Europe, and Northern Asia. And we can deliver and support such scales mostly because we have the S3 partner network, and that's over 2,400 partners, right? 400 of which serves water organizations. For instance, Schneider's Electric's Cytex SCADA, and ArcGIS, hydraulic modeling, Autodesk for your computer-aided design, CAD, and BIM, your building information modeling plans, Oracle for your database management systems or enterprise asset management, and so much more. Now, as partners, we aim to draw on their expertise, and you can be sure that the integration is improving every day. Now, moving on to what GIS is for water. Now, if you're here, you might already be familiar with the term, but otherwise, it's geographical information systems, a way of using location intelligence to improve your work. Now, ArcGIS is a comprehensive geospatial system, and it supports multiple communities, primarily the GIS community, but also mapping and location analytics, imagery, and also for developers. And we do this, of course, with software and software as a service, SaaS, and platform as a service, PaaS, powering personal productivity and also enterprise systems. And our vision supports a whole host of functions that aims to power your organization with modern and applicable tools to make sense of the great volume of data available these days. Now, ArcGIS is a content sharing platform. What that means is millions of users are sharing tens of millions of maps and data sets every day. And it's been designed to allow maps and data sets to be easily discovered and then easily shared in a secure environment for both public and private use. And our hosted data cloud is massive, with multiple terabytes of information and multiple petabytes of imagery, making this a key concept and aspect of geospatial infrastructure. And you can see that the sources of data on the left-hand side here spans across multiple industries and expertise, such as bathymetric data for radar or digital elevation models using LiDAR. And you also use big data analytics during floods, for example, to mitigate or even calculate the damages in real time. Or use time-based location analytics for water usage, along with development initiatives to predict water demand. And the use cases goes on, right? So before I continue, just a reminder for you to ask questions whenever you have any doubts. You can type it into the Q&A panel as we go along. But now I'd like to bring you back, right, to a perspective of the local water supply system. And you might be aware that these are being controlled by the National Water Services Commission under CASA, the Ministry of Environment and Water. And it's an intricate network, right? It involves a lot of stakeholders, regulators, operators, all the way to the consumers themselves. So let's have a look. So in this illustration of an intelligent water system envisioned by Esri, all systems are connected and modeled in detail, much like a digital twin of the actual network. And from the source of water, such as rainfall and raw water catchments, you have JPS, Jabatan Pengairan dan Saliran, the Hydrology Department of Malaysia, SAN, the Water Services Commission, and some state water commissions regulating these areas and maintaining the quality and sustainability of development. And when it passes into production, right, for water treatment and distribution, right, you have water operators like AIS Selangor, which is for the state of Selangor, PBAPP for Penang, Syarikat Air Johor for Johor, of course, and so on, right? And that would include the reticulation phase where clean, treated water is supplied to industrial and domestic consumers. Now, we also have IWK, Indah Water Consortium, on the right-hand side here, to help us manage the wastewater and discharges. Now, ideally, this is what the entire modernized utility network looks like. And you have delicately modeled systems that are connected, and it supports the operations and sharing of information among one another. And each of these components have challenges, right? And some of them overlap. Let me illustrate that. So in every initiative to drive digital adoption, we want to start with identifying the key people who will be using it day in and out, right? We start with the people. And that ranges from the general public who can provide you with consumption data to field workers, right, updating asset information during maintenance, and the analysts and engineers performing the analysis and making it usable. And then all the way at the top, you have the executives and the key stakeholders who make impactful decisions. So in this sense, the entire journey of digital transformation covers the entire hierarchy. And the key challenges to tackle revolve around three areas. Now, real-world modeling, representing the real world digitally, will pose many challenges, right? From modeling the intricacies of a booster pump house all the way inside, right? Or a network of pressure management valves, to modeling the utility to the extent of being able to delineate subnetworks, such as district metered areas or pressure management areas, which then enables these directional flow analysis and constraining areas to scrutinize your non-revenue water, your percentage of water loss. And when you put these all together, they allow you to generate traces within your network, helping you to support emergency shutdowns, follow contaminants to their sources, and so forth, right? Or there could be challenges relating to integrations with multiple systems. For instance, communicating with IoT devices such as remote terminal units, RTUs, or leak detection equipment such as acoustic leak detectors, or an enterprise asset management system, right, that you have invested millions in, now paired with a GIS to help you be more proactive in the asset maintenance or tracking asset life cycle to understand various types of assets and the behaviors for rehabilitation or pipe replacement initiatives. And you bring them all together with spatial statistics, with advanced tools such as Python model builders to automate your work. Excuse me. Now, another very real factor in digital transformation is about bridging the gap between field and office, where you want to be able to use any device, whether in connected or disconnected environments, and be able to manage tasks based on regions of operations, to collect real-time data and bringing this information into a dashboard, right, with up-to-date views of your resources and key performance indicators. That's plenty, right? And that just brings all the previous angles of working towards realizing a digital twin via a framework known as a geospatial infrastructure that is location-centric. Now, from the perspective of an operator or regulator, this can be done from scratch or to complement existing systems or data sets or CADs in your organization. Now, the geospatial infrastructure works by first assessing, documenting the locations of all types of data sources, instruments, imagery, land administration plans, as-built drawings, and so forth, right? And then there's integrating with multiple types of systems providers. And in the case of water supply services, it will be SCADA, a supervisory control and data acquisition system, hydraulic modeling systems, asset management systems, billing or consumer information, and so on. And from this point on, depending on the input, you can begin designing and building a variety of applications and systems capable of serving a large consumer base as a single source of truth. Now, from our experience visiting a number of state water operators, each department will have their own needs, their own organization charts, their own way of doing things, their own processes, and some applications will cater to all sections or just some specific sections or departments due to the authoritative nature of the data set. And in the water and wastewater fields, thousands of organizations around the world are embracing GIS as a foundation for everything they do. So from the top left, GIS is used to monitor water consumption for different DMAs. It could be trade, it could be industrial, it could be commercial or domestic. And NRW, non-revenue water improvement projects are targeted, right, at areas with high water consumption or high water loss to be in line with the operator's sustainable management initiatives. Now, coordinating operations can be a challenge these days, and traditionally it's common to use clipboards and pens to collect data outside in the field. And then you have to go back to the office or in your car and digitize it using a computer in a form of database or Excel sheet, right? Or using WhatsApp to communicate maintenance statuses of thousands of valves. Just try to imagine that. It's going to take a while. Now, GIS is being used by field workers of many water operators worldwide to carry out inspections, maintenance works, and monitoring irregularities in static pressures. That may be contradicting with head loss, right, of a storage tank, for instance. Now, the interesting example from New Zealand at the center bottom here shows wiring together SCADA systems with GIS and BIM, building information modeling, of which the data source could be Revit, could be project management softwares, and giving a new dimension to the whole world of wastewater. Now, for the first demonstration, I'd like to present an example of integration with a portion of SCADA system based in Naperville, Chicago, USA, as a means of being prepared for emergencies, anomalies of water supply, and execute corrective measures within reasonable response time. So let me bring them up. So in this tank level dashboard, connected to a SCADA system, on the left-hand side, you can see that there are three, right, tank alarms. And the tank volume is actually a percentage of the entire storage capacity of the tank in height. So if you look at the bottom here, current water height in tanks show that now there are about, about quite a few water tanks here, and generally you can also put a 20% water storage capacity, which means that when it actually drops below 20 or at 20, there will be an alarm coming up. An alarm such as this. So if I click on one of these examples here, it will bring me right to where I need to go. And it does show me here that it's at 11.25% capacity, and that's alarming for good reason. Now, the next step for integration or automation in this case could be creating a notification out of this, which means that whenever it drops below 20% or it's at 20%, and a notification, an email or a Telegram message could be sent out via Power Automate or Integromat to the water operator and the person in charge. So that ends the short demonstration on this SCADA water tank. And now that we've witnessed the SCADA integration, we'll take it a step further in the perspective of asset maintenance. So the question water operators, especially in different regions, areas in the planning department, will need to ask is rather often is, which areas are affected, right? If I were to replace a certain valve or a section of a pipeline that has burst, for example. So let's have a look. Right. So in this example, I'm just trying to look for an asset maintenance. So for example, I'm a asset maintenance guy, and I want to be able to see where will we actually, which area will actually be affected if I were to create an asset maintenance program and replace a certain pipeline. So I'm going to look for this BB Elementary School. So I can just search for this location, and now that I found it, I'll just take it away. And I know that I'm going to create a sort of program to replace a section of a pipeline here, which I know has been leaking for a while. So I'll just place a barrier here, right? And I want to make sure that I'm tracing from the elementary school so that it's not actually affected, and especially when I'm actually doing maintenance work. So I'll run it, and it'll take a while. So I've actually done it previously, and this is how it looks like. So you have an orange area that represents the area that will be affected. You've got those red color, no entry signs. That means these valves have to be closed. I know that the elementary school is not going to be affected. And the hydrants, there are two of them that will go without service during the maintenance, during the pipe replacement work. And if I just look at one of this, I know that this is a ductile iron material or pipe. So at the same time, I can also print this as a map. I can go on and try to create different isolation traces, so to speak. And this is one way that you could plan ahead when you're trying to do asset maintenance programs, and you can inform those people who might be affected in this yellow region. So that ends the demonstration for utility network isolation trace. So let's continue with some use cases, right? And GIS centric solutions are increasingly used in the water and wastewater sector, and with multiple organizations leveraging on location intelligence to solve everyday issues, not just in water. But focusing on water now, from the clockwise, I'll go from top left, from asset management perspective, analytics, real-time monitoring, to infrastructure assessments. All right, and GIS is being used in many key components to ensure the consistent delivery of clean water to users. But in the realm of assessment, right, center bottom, ArcGIS supports online and offline field inspections, right, using an intuitive and mobile optimized application in both iOS and Android to collect and update field information. And another reminder now for you to ask questions. I know you have some in your mind, so I'll go easy. I'll have a sip of water and you can type the questions in the Q&A panel. And after this, we have a look at an example. All right, let's go on. Having a look at an example. So in this scenario, a team of field workers are always tasked to inspect a river network that is infamous for pollution. And that could be responsibility of the state's water regulatory body, such as SWAS, in the state of Selangor, or the initiative of the state water operator itself. And this covers work order planning, which is another trade unto itself, and visualizing spots of contamination as alarms, signifying water quality compromises according to the National Water Quality Standard. So let's have a look. All right, primarily, I will start with a workforce assignment platform where I begin to assign jobs to people. So in this map, I can really see that there are quite a few assignments being put out here by myself and also my colleague. And in this assignment, I can pick assignment types. Maybe it's a river investigation. I can search for an address which will be reverse geocoded and pointed into the map, or I can just point at a location and it will actually appear geocoded. I can assign it to myself or whoever else in an organization, create a priority, due date, time, an ID descriptions, and I can also add attachments by selecting a file. Once I've created the assignment, the field workers should get a notification. But on the field workers' perspective, right, they will be able to start with a smart form, right, which is a dedicated form to their purpose. And this is just for river inspection. So we've got the main river, right? These are all been pre-filled. The sampling point status, audio pollution. I can capture an image, upload it into it. I can even add locations or change location. This is coming directly from where it was in the assignment. And I can submit. But otherwise, I can also include QR codes in this form. I can include signatures and whatnot. So once the field workers actually input information into this form, it can be shown in a very simple graphical user interface for this form's data, right? And you could even create a report from it straight away, or export this as different files if you need them. But finally, the output for stakeholders or executives would be a dashboard, right? And this is a simple dashboard illustrating the points that have been collected during the river investigation. Now, these are indicators on the left-hand side. Blue for sampling points, so that 11 so far. Critical points that could also be in lists, and non-critical points, which will show me that they are all okay. Now, if I want to focus on one of these rivers, I can select it and it will zoom right down to it. And I know at this area, I've had a historical data that shows me that there's been some pollution at this area. In this picture here. Now, it can also be historic, meaning that this could be, taken in the past quarterly basis, monthly basis, and you could trend it and sort it new to old, which means the most recent reports will come out first. As simple as that. So that ends my demonstration for this river pollution inspection scenario. And I'll move to another scenario, which is, in the previous example, we covered sort of hard to reach areas that might not have good cellular reception and or areas that require sampling only at quite long intervals, right? But how about if you had water quality analyzers, right? Instrumentation and RTUs that are able to alternate routine inspections, right? You have integrated with these RTUs that will monitor for NTU, your turbidity levels, your E. coli, salinity, aluminum, and such, right? And this would help you to steer towards environmental stewardship, right? For water supply security, for watershed protection and conservation, and so forth. And even coming up with recommendations. So this example is actually from British Columbia in Canada. And what they've done is created and integrated all these water quality analyzers that look at E. coli and different other parameters. And the best thing here that I want to really highlight is that they've also automated this recommendations, right, to reduce fine sediment generation. What ArcGIS dashboard can do is do on-the-fly calculations using arcade expressions. So what it does is, from the parameters that have been come out, let's say there's high E. coli in one of the water quality analyzers being detected, it will actually come out with a proposed recommendation for that area, and it will actually show how many of them are actually having low impact ratings, right? Or low impact ratings or high impact ratings. For example, we can filter it quite easily. If you want to have a look at it, this is actually public, and you can probably have a look at the dashboard just by using the URL. So that ends my demonstration for water quality dashboard. And that was probably quite a bit to digest, so I'll let all the information we shared just now sink in, right? And we will also revisit some of the concepts, so you'll be able to have a take-home message with you. And GIS at the center facilitates all the integration, the coordination and analysis of disparate hardware and software, workers and processes and departments and data sets across space and time, right? But the genesis actually stems from the multitude of data sources that can be consumed to synthesize into useful information and updated from time to time, leading to a geospatial infrastructure capable of creating the most advanced solutions to solve your water challenges, right? Whether it is water loss, your asset replacement strategies, increasing your reserve margin, protecting your watersheds, or improving your risk management through capital planning improvements, and so forth, right? So from here, we really want to encourage you to start leveraging on the language of your utility, right? And bring it a step further to enable better decision making through collaboration, and which is surrounding an authoritative single source of truth illustrated by this geospatial infrastructure in the middle. Now, as you can see from the 4 demonstrations just now, ArcGIS delivers modern asset information management capabilities to a water utility and enables full coordinate approach to operations. And all of the examples we have looked at just now, I want to ask you, which ones are actually your favorite? Right? Is it the SCADA integration? Is it workforce management for river health inspections? Is it isolation tracing for burst pipes? Is it real-time information from water quality analyzers across state? All right, I'll let you take your pick. However, we must keep in mind that the underlying technology must help the organization collaborate more effectively within and outside of it, right, via an authoritative data set, which data integrity can be maintained and then served through a comprehensive data log via a services-based architecture. And this will help every level of users to improve their awareness while maintaining cost efficiency throughout decades of operations and scalability to keep up with increasingly complex requirements such as cloud deployments, Kubernetes, and so forth. And with that, I'd like to wrap it up and invite you to contact our industry account manager, Jaylin. She's based in Malaysia. And if you have any inquiries, we hope and we will do our best to assist you in the future. So if you have any questions, we would like you to ask. And thank you for your attention so far. And I know there was a lot to capture. Now, we have had a couple of questions come through, and you've been listening intently and you haven't had a chance to type out your questions. There's still some time, so you can do that in the questions pane. All right. All right, so we've had a couple of questions come through. One of them has asked, how do you actually put NRW in a dashboard per se? To answer that question, we have to bring it back to sort of a performance measurement of non-revenue water. In short, it's NRW. So NRW is usually measured through system input volumes and consumer billings and the difference of it. You can actually do that through algorithms. I believe there are algorithms out there that are readily available through the International Water Association based in US. You could use theirs. I'm pretty sure your operator, your state water operator, is probably already using that. But the other perspective is from there, you could actually expand it into a map, into the dashboard that shows what's the NRW for each of the district metered areas, or each of your regions or your states if you're a National Water Services Commission, such as SPAN. Right. On the other hand, you could also use infrastructure leakage index, which is if I remember correctly, which is a difference between a ratio between current and unavoidable annual losses of water. And that could be a modern way of doing it, but it may not be so applicable in an area sort of manner, because it calculates by kilometers of pipes or pipe burst index. So there are many ways of measuring performance of water losses, but that's just one example. Hope that answers your question. Right, and there's another question that asks, in general, what affects the asset performance of a water utility? Well, there's quite a few. There's quite a few, and the performance of water utilities and their assets are mostly related to the percentage of water loss, right, which is a measure of your asset health. And that could be just one of the factors. That could also be pressure management. So incidentally, if you have high pressure, you have high loss, right? If you have low pressure, you have low loss, but that also means that you have to manage it so that the end consumers, the consumers at the end of a pipeline, for example, won't actually be complaining every time during peak hours when they will not be getting any water. Or it could also be the effectiveness of your operations. If you have a fast turnaround time of asset maintenance programs, pipe replacement programs, for example, or pipe rehabilitation, so you're changing from asbestos cement to mild steel or HDPE, for example, you would be able to turn around quickly and have a skilled team that actually updates that information as well. Or it could be using active leak control systems such as acoustic detectors to, identify where these leaks are and be able to address them appropriately. So, all right, that's all the time we have for today's question. If you have more, please do not hesitate to reach out to us, and we will reply you with the answers as soon as possible via email. All right. So as a reminder, we have recorded this session. So a link to the recording plus any other resources will be included in our post-event email that will hit your inbox early next week. So keep a lookout on the next Directions Live online webinar. We really love your feedback, and that will help us to improve as well. So please take a moment to fill out the brief survey that we will see pop up at the end of the session. So thanks again for joining us today. We really look forward to seeing you again for the next webinar. Goodbye.